American Geophysical Union. With that, let me pull down my slides and turn the meeting over to Dr. Williams.
All righty. Well, thank you very much for that nice introduction. If you can enable me as a co-host, we'll bring up my slides. I'm speaking on behalf of our principal investigator, Dr. Lindy Elkins-Tanton, who apologizes for not being available to speak to you. She asked me to go in her stead. She is very heavily, we're in the development of the Psyche spacecraft. We're in phase D. We're in what is called ATLO, assembly, testing, and launch operations to get the spacecraft ready for launch in August of next year. So that's what's occupying her right now. But I'm happy to speak to you in her place about the Psyche mission. So I will see if I can share my screen and bring this up. And I'm going to put this in full screen mode, and somebody's in the waiting room to admit. And so I just admitted them. And what I'd like to do is to go through my presentation. If you have questions, please make note of them and hold all questions till the end of the presentation. And I'll be happy to do a Q&A as long as you folks like. So,
hey, David, this is David Wood, the host of the meeting. I'll go ahead and take care of anybody coming in the waiting room, okay?
Excellent. Thank you very much. I'll just turn my volume up a little bit there. And what you're looking at on the screen is some artwork that was made about the Psyche mission. And you see two planetary objects colliding with each other. And we think that is the essence of the story about Psyche. And we'll explore that here. This is my title slide here with a nice artist concept painting of the actual Psyche spacecraft as it's going to look. Actually, as it does look, because the main body of the spacecraft is at JPL right now. And I'll show you that later. So when I talk to public groups, particularly the groups I speak to the first time, I like to step back a little bit from the story of asteroid exploration and Psyche and do something a little bit more fundamental. Why do we explore space? Why do we want to explore the solar system? As you can see in this slide, there's a whole host of reasons that we do it. As scientists, we're interested in the science. We want to understand the cosmos, the universe, what it is, what makes it up. But there's a variety of other reasons why we choose to explore space. We do it for national prestige. Great nations undertake great things. And arguably one of the greatest things that's been ever done by a nation was to send humans to walk on the moon, something the United States can be justifiably proud of. We also explore space for security. We want to maintain the high ground. We want to protect ourselves from adversaries. We do it for economics. We want to be able to identify and exploit space resources, something that can enhance our national economy and help create a spacefaring civilization. We do it for sustainability. We want to develop new technologies to better preserve Earth and its citizens. We do it for education and inspiration. We want to help create and develop the next generation of scientists and engineers. And both of these reasons are linked because, we live in a society that is increasingly reliant on science and technology and using science to understand great problems. But we live in a society where there isn't a strong background among the general public in science. And so this is something that we want to try and alleviate through space exploration. And then final reason is survivability. We want to transform humanity into a multi-planet species. The reason why the dinosaurs aren't here is because they didn't have a space program. They couldn't detect that asteroid that struck in Mexico 65 million years ago that wiped them out. And the surest way to avoid that fate happening to us is to have humanity on multiple bodies and locations throughout the solar system. Now, what is NASA's role in exploration? Well, NASA actually has, it's actually 5 now. I have on the slide 4 mission directorates. Aeronautics research studies the air transportation systems and helps supports that. The Space Technology Mission Directorate actually develops the technology for people to live and work in space. The human exploration and operations part of NASA is the part that you hear about the most. This is with what was the space shuttle, the International Space Station, the Space Launch System. That involves the human work in space. But there's another division called the Science Mission Directorate, and that's the one that funds all of the scientists and engineers who do work related to space to understand it from a scientific perspective. And the Science Mission Directorate splits the cosmos into 4 divisions. Heliophysics studies the sun, Earth science studies the Earth, planetary science studies everything in the solar system except the sun and the Earth, and the astrophysics division studies everything outside the solar system. So every NASA scientist who does planetary work has been funded through the planetary science division. I should also say that about a fourth division down here, that's actually biological and physical sciences, which was just formed relatively recently. So how do we explore the solar system? NASA uses robotic spacecraft by and large to explore the solar system. How do we choose what spacecraft to use to explore a given body? Well, it turns out there's a logical thinking about how we do this. We do it in a phased approach. We do what's technically possible, what we have the engineering skills to do and build. We do what's affordable, what Congress will give us the money to build and accomplish. We do the easy missions first, we accomplish them successfully, and then we move on to more complex missions. And this list below is the types of robotic missions leading in increasing order of difficulty and complexity. The easiest is a flyby mission. This is where you launch a spacecraft from Earth, it flies by a planetary body, takes pictures, collects data, transmits back to the Earth. This is what you use for the initial reconnaissance of a new object. This is what the New Horizons mission to Pluto was back in 2015. After you've done that, then you want to send an orbiter mission. This is to actually get a spacecraft that will be able to slow down, get into orbit around a planet, and then as the planet rotates underneath it, the spacecraft acquires data, and this gives you your global data set, gives you your global assessment of a planetary surface. So once you know about it from orbit, then you want to head down to the surface. So you'll want to land, and there's a variety of landers. Hard landers are ones that descend, and they're going really fast, and they smack into the surface, so you have really limited data. We tend not to use those. Rather, we prefer soft landers that use retro rockets and parachutes or airbags or something that can slow it down. The spacecraft lands on the surface, the instruments are all intact, and you can get your data from the surface. Now, typically, when you land on a planetary surface, you get a 360-degree panorama of your landing site, and as sure enough, you find something interesting over there, and you wish you could go there. So this is why they developed the ability for mobility on a planetary surface, and this is what NASA's rovers are. So mobility on land, or if it's a body that has an atmosphere, it can be something that could go through the atmosphere. And the Dragonfly mission to Saturn's moon Titan is something that's going to do that. And then the next hardest thing to do, the next most expensive, is what we call sample return. This is where you send a robotic spacecraft to collect a sample of rock or soil or dust or ice or atmosphere, bring it back to Earth where it can be studied more efficiently in our laboratories here on Earth. The next one is an orbiter or lander for one of the icy outer moons of the gas giant planets. I include this in here because it's really, really hard to get a spacecraft to slow down to get in orbit about a gas giant and to move into orbit around one of these planet signs of moons. It just takes an awful lot of effort. And then, of course, the most expensive and the hardest thing to do are to send humans, crewed missions, to orbit and land on planetary bodies. So with this slide here, this sort of summarizes the state of solar system exploration as it is here in 2021. You see across the top the various modes of exploration, starting with telescopic observations, which is how they're discovered, all the way out through the types I just mentioned. And then we start with Mercury and the inner solar system all the way out to Pluto and the Kuiper Belt. As you can see here, everything was discovered by telescope. We've completed the initial reconnaissance of the solar system by flyby, thanks to the New Horizons mission, which visited Pluto in 2015, and then went by Arrokoth, the cold classical Kuiper Belt object, in January of 2019. With orbiters, we've sent orbiters around all of the inner planets, the inner rocky planets, around asteroids and comets, and we're gearing up. We sent them around Jupiter, of course. Juno is currently orbiting Jupiter. We sent Cassini to Saturn. We're starting to fill it in with some of the other outer planet bodies. The Europa Clipper is in preparation for launch, which will be a Jupiter orbiter, but it will still get global coverage of Europa. The JUICE is the ESA mission, European Space Agency's Jupiter Icy Moons Explorer. That is actually going to be a Ganymede orbiter mission. I should say these missions that are in green are either in flight or in development. White are things from the past. Yellow and orange are things that have been proposed but not fully funded or developed yet. As we move along the chart here, you see we have landers on a lot of the small bodies, inner planets, the atmospheric probe into Jupiter from Galileo, the Huygens probe that landed on Saturn's moon Titan. Rovers, we've had the very successful Mars rovers with Sojourner, Spirit, Opportunity, Curiosity, and Perseverance. The Soviet Union had the Lunokhod rovers on the moon back in the 1970s. We are also preparing the Dragonfly, which will be a drone for Saturn's moon Titan. Sample return, the Soviets had robotic sample return from the moon in the 70s. We're preparing for the Mars sample return campaign, which will dominate this coming decade. OSIRISRex and Hayabusa 2, the Japanese mission, are sending samples back from Bennu and Ryugu, near-Earth asteroids. And then finally, you see the one that's least filled in are crewed missions, because we've just had the Apollo program to the moon. So what I like to tell people is our goal is to completely fill in this chart, completely explore the solar system, and then we'll be able to do, as they say in Star Trek, boldly go where no one has gone before. So with that preamble, I'd now like to get into the bulk of the talk there and talk about asteroids exploration and the Psyche mission. So a little background on asteroids and why Psyche is of interest, give you the details of the development of the Psyche mission, its objectives, instruments, and how we're going to explore Psyche, and then a look ahead at some of the other things before I go to Q&A. So asteroids, what are they? Asteroids are minor planets. They're protoplanets. They tend to have diameters less than 500 kilometers in diameter. They're mostly irregularly shaped, like this picture of asteroid Lutetia from the European Rosetta mission. They tend to be composed of silicate rock, dust, and what we call volatiles. Now, volatiles are basically ices, mostly water ice in the inner solar system. As you move to the outer solar system, you can get more exotic ices like carbon dioxide. There's an open mic there for somebody. Additionally about asteroids, where are they? Well, most of the asteroids are located in the main belt, located between the orbits of Mars and Jupiter. There's also a population of asteroids at the Lagrange points of Jupiter's orbit about the sun, the Trojan asteroids, and we're preparing a mission to launch in October and November called Lucy, which will explore these asteroids for the first time. Centaurs are asteroids beyond the orbits of Jupiter and Neptune. And of course, the ones that you probably hear about the most are the near-Earth asteroids. And there's several variety of those. These are the asteroids whose orbits come close to or across that of the Earth. There's about 4,700 of these potentially hazardous and near-Earth asteroids, because they're the ones that can potentially impact the Earth. And over the course of the last decade, there have been plenty of examples of these. Here is one that 2012 DA14 occurred on February 15, 2013. You see the radar shape of it there. It's irregular. This asteroid flew in. This is a pretty close approach. Above the orbit of the International Space Station, but below the orbit of the geosynchronous weather satellites. Came in south to north, not visible from the USA. It was imaged by Goldstone. That's the image up at top. And you can see the graphic there below. This was about 45 meters long asteroid, same size as that, which made Meteor Crater in Arizona, my home state. So Meteor Crater is about 1,200 meters in diameter. Meteor Crater is about 170 meters deep. If this asteroid 2012 DA14 hit, it would have had an energy of 2.4 megatons, destroying everything surrounding 50 miles. It's not big enough to end civilization, not like the asteroid that struck Chicxulub that killed off the dinosaurs. That was 180 kilometers in diameter. Or excuse me, it formed a 180 kilometer diameter crater. The impactor was 10 kilometers in diameter. So, you know, these things are something that we need to be aware of. That very same day, February 15, 2013, is the date of the Chelyabinsk strike in the atmosphere above Chelyabinsk, Russia, the largest meteor strike since the 1908 Tunguska event. Entered the atmosphere very fast, 17-meter diameter, 10,000 ton mass, but this one came in west-east, so we know it's not related to 2012 DA14. This one was an airburst, 12 to 15 miles above ground. It had a 500 kiloton shock wave, and you recall that it went out and it damaged buildings and caused about 33 million in damage. This was an ordinary chondrite type of thing. So this is, you know, we're concerned about these things, and that's why NASA has a near-Earth object observation program to try and identify and map the largest to increasingly smallest size of these objects so that we can identify them. This one was quite interesting. A2017 U1. This was an extraterrestrial asteroid, something that came outside the solar system, and you saw the graphic as it flies by the solar system, discovered by Pan-STARRS in 2017. It's more commonly known as Oumuamua from its Hawaiian roots there, and there's been ideas about it here, and you see the shape of the asteroid, something from out of the solar system. I think our recent research suggests it's probably something similar to a Kuiper Belt object, but from somewhere else in the near part of the galaxy. So anyway, we're interested in understanding NEAs as well. So what else do we know about asteroids? Well, it turns out there are 14 types of asteroids based on the reflected light telescopic spectra. The largest class are the C-type. These are dominated by carbonaceous materials. S-type are the stony, about 30-35%. There's D and P, dark and primitive. V-type is what asteroid 4 Vesta is. It has basaltic minerals found in lava flows like in Hawaii. And then there's the M-type. M in this case means metallic, iron, and that's what Psyche is. So based on the spectra from the reflected from the asteroids and study of meteorites in laboratories, because meteorites are pieces of asteroids, the predominant theory is that asteroids are rocks that never coalesced into a planet. The gravitational tugs of Jupiter affect that location of the solar system and never would have allowed a planet to form. So that's what we know about asteroids. Now, how many missions have we sent to asteroids already? Well, here you see the chart of, and this is all of them that I'm aware of. I was actually in grad school at Arizona State in the 1990s when the Galileo mission on its way out to Jupiter flew by 951 Gaspra and 243 Ida, the first asteroids that we actually imaged by spacecraft. Near at 433 Eros was the first asteroid dedicated mission, an orbiter. And you see that there's been quite a few since then. And then at the bottom in bold are missions Dawn, which I worked on last decade to study Vesta and Ceres, the Hayabusa missions, OSIRIS-Rex, which is both of which successfully acquired samples and are returning those to Earth. And then the two latest Discovery class missions, Lucy to explore the Trojan asteroids, and then Psyche to explore asteroid 16 Psyche. So this chart here, this is a chart that was made of all the asteroids and comets explored prior to the Dawn spacecraft arrival at asteroid 4 Vesta in 2011. And you can see the asteroids are irregularly shaped, heavily cratered. You see that they have boulders on some of them. They have lineations, perhaps indicative of tectonics on them. But they're large rocks in space when you look at this particular size level. And Lutetia is 132 by 101 by 76 kilometers. So this is the biggest one that's seen at the time. Now, when you compare asteroids with planets, here's a comparison between Mars, Mercury, and the Moon, all at the same size scale, and dwarf planet Ceres and asteroid 4 Vesta at the same size scale. So we're getting to much, much smaller planetary bodies. Now, why do we care about asteroid Psyche? Psyche was the 16th asteroid discovered. It's the largest M-type asteroid in the solar system. The images on the right show the shape of this, and you see it's not round. It's actually more potato shaped, and that's probably because of the impacts that have struck it. 279 by 232 by 189 dimension on there. It's discovered by Hannibale de Gasparis of Naples, the Naples Observatory in 1852. Psyche orbits at the edge, the outer edge of the main belt at 2.9 astronomical units. I don't need to explain that. You're an astronomy club. Orbits in 4.99 Earth years. It rotates on its axis in about 4 hours. What is Psyche composed of? Well, M-type asteroids are thought to be the source of some iron meteorites, which are thought to be some sort of a planetary core material. Very dense, solid body, could have some porosity, some regolith, very primitive materials, mostly metals, some silicates. There could be some amount of water ice deposited on comets. That's something we're going to look at. And here's just an example of some of our favorite iron meteorites here. You can see down at the bottom a very typical iron meteorite, and then up at top you see a Pallisside. A Pallisside is thought to be from a core mantle boundary where you have the olivine grains completely surrounded by metal. So those are the analogs that we have for Psyche right now, something related to the iron meteorite various families. So Psyche has been studied up to this point through Earth-based telescopes and various other ones. How big is asteroid 16 Psyche? Well, here you see a chart, and you can see on that first chart I showed where Lutetia was the biggest one. You can see that, and some of these others are very small compared to asteroid number 4 Vesta, and Psyche is basically in between. Here's the Psyche shape model right over here. So it's bigger than Lutetia. It's not nearly as big as Vesta as studied by the Dawn mission. To give you some a little bit better indication of its size, it's basically the size of the state of Massachusetts if you leave off Cape Cod, or the distance between Phoenix and Flagstaff, Arizona. And here's just another graphic to show this. And so you see Vesta and Psyche along with Eros and Bennu. Bennu is the dot in the smaller square there that was just sampled by OSIRISRex. So we're talking about a pretty good sized body, but not the biggest ones that we have out there. So the NASA Psyche mission was conceived through the proposal opportunity to NASA's Discovery Mission program. And the driving question about this, the first M-class or metal asteroid to be explored is 16 Psyche the core of an asteroid parent body? Here you see the shape model of it again, something that's been pummeled. And we have 5 definitive science objectives we want to accomplish with the Psyche mission. Is Psyche, in fact, an ancient planetary core, or did it never undergo melting? What are the relative ages of materials on the surface? Do small metal bodies incorporate light elements expected to be inside Earth's high pressure core? In other words, can we study this as an analog to what the Earth's core might be like? Did Psyche form under more oxidizing or reducing conditions than the Earth's core? And what is the topography of a world made out of metal? These are the things that we hope to answer through the Psyche spacecraft. So the concept about this particular asteroid is that early in solar system history, we had the small bodies in the solar nebula that were banging against each other and accreting to make planetary embryos and eventually make planets. The idea is that some of these may not have been hit directly, may not have coalesced to form a planet, but rather you had what are called hit and run impacts, where something that had been separated into a crust, mantle, and core through this hit and run impact would have knocked off most of the crust and mantle and leaving the metal core behind. And that's what we think Psyche is. And here's a cartoon that basically shows that. You see a differentiated into a crust, mantle, and core planet there, hit by a side-on impact, knocking off most of that. You have your molten metal that starts cooling. It'll have a magnetic field because it's molten metal. And then as that continues to freeze in, and it preserves the magnetic field in the surface materials. So what does the Psyche spacecraft look like? Well, it looks a lot like an Earth orbiting satellite, but it has various things added to it. So you see here a high gain antenna for communication. There's also a low gain antenna. It has a couple of booms on it. One boom is for magnetometers. One boom is for the gamma ray and neutron spectrometers. The DSOC is on this side, and then on the back side, the negative x-axis is where the 2 imagers are going to be. And then down here, you see the ion thrusters, which I'll talk about. So compared to a person, you see that the Psyche spacecraft, when you unfold the solar panels, is about the size of a tennis court. So the mission, the way the mission is going to operate is we're going to launch, hopefully a year from now, in August of 2022. Chemical rocket will take the spacecraft out of the Earth's gravitational pull. And then we're going to fire up our ion thrusters. This spacecraft, as the Dawn spacecraft from the previous decade does, it uses solar electric ion propulsion to power the spacecraft. And where you have the gray along the orbital track there, that's when we're actually firing the thrusters. And we thrust for long periods of time to build up the momentum to get out to the asteroid. These type of spacecraft spiral around the sun as they go ever outward to get to the target body. Now, you mentioned the DSOC, the Deep Space Optical Communications using laser optical communication testing. You see these blue points on here. Those are actual times we're going to be testing the DSOC as we get further and further away from Earth and out to Mars, so that we can actually test and see whether laser optical communication would be an effective method of communication as a backup for our existing antennas for when we go to Mars. So you see the spacecraft will do a Mars flyby in May of 2023. This will give us an opportunity to test all of the instruments on Mars to make sure they're working properly. And then the spacecraft will continue thrusting until it gets to Psyche in January of 2026. So that's a 3.4-year cruise phase to get out there. And then we're going to have 4 orbital phases, A, B, C, and D, as we collect all the data. And then the nominal mission will theoretically end near the end of 2027. So I mentioned that this spacecraft uses solar electric ion propulsion. The idea behind ion propulsion is that you have a xenon as your fuel source, and an ion engine uses very small amounts of that fuel per time. It's the exact opposite of a chemical propellant, where you have big fuel tanks, you fill them up with this stuff, you burn it very quickly to give you a boost. It'll get you there much faster. But the idea of an ion engine is you slowly burn this lower amount of mass on the fuel on the spacecraft. You fire your thrusters for long periods of time. You slowly build up your momentum. So that's why it takes longer to get out to where you're going. It takes longer time, and the thrust is a lot lower. But the advantage is you don't have to have all that heavy fuel on board. That reduces the mass, which reduces the cost of the mission. The Dawn mission and the Psyche mission could not have been done if ion propulsion didn't exist, because the amount of fuel mass to get out there would have been too great, or it couldn't have been done as a discovery mission. It would have cost much, much more to get out there. These Hall thrusters are something that Maxar Technologies have used for many times. You see all these diagrams here around Earth. These are all individual satellites, Earth orbiting satellites, that have used these Hall thrusters form of ion propulsion to study the Earth or can help communicate with the Earth. So this company, Maxar, has a long history of building ion-powered spacecraft. This is the first time they're using this for a deep space mission. So when the Psyche spacecraft gets out to the orbit of 16 Psyche, we're going to go into a variety of orbits. And each one of these orbits, starting at a higher orbit and working our way down from A to D, is optimized to collect data for each of the instruments. So when we arrive at orbit A at 700 kilometers altitude for 56 days, we'll be getting our magnetic field measurements of the asteroid, determining whether Psyche has a remnant magnetic field or whether it's unmagnetized. We'll do our first imaging of the surface to get the broad geological structure of the asteroid. And then from that, we'll move down into orbit B at 290 kilometers altitude for 80 days. This will use the imagers in stereo mode to photograph the surface. And by looking at the same surface from different look angles, you can make a stereo-based digital elevation model that'll give us the topography of the surface. And we'll also be doing geological mapping of the features and counting the impact craters and looking for colorations that might indicate different types of minerals. As we move down lower to orbit C, 170 kilometers altitude for 100 days, this is when we'll get high resolution gravity of the body. And the way we do that is, as a spacecraft orbits a body, if there's a location in the body that has a greater mass, that does a slight tug down on the spacecraft, and you can precisely measure that with the Doppler time delay of the radio signals back to Earth. And that allows you to build up a gravity map and also to get information on the interior configuration of the body. We'll also be doing a higher resolution topography measurements and magnetic measurements. And then finally, in orbit D, we drop down to 85 kilometers altitude for 100 days. And this is where the gamma ray and neutron spectrometers will be put to use. They will get the highest resolution possible of the elemental abundance of materials making up the surface. And if there's hydrogen present as a proxy for water ice, that will also be able to be measured as well. And continuing on, this shows you the operations for the orbit. So we have an approach phase. During the approach phase, we're going to be looking at Psyche to make sure it doesn't have any moons, because asteroids do have moons, some of them do. And it gets very bad if you have a spacecraft and you go into close orbit. And there's moons around, so we want to make sure we'll be able to map and avoid those. I really doubt that they will be there. They haven't been there around other of these big objects. But then, as you can see, as I just stated here, we'll go over orbit A characterization, topography, gravity science, elemental mapping, etc. And I've also included here the image resolution of our images. So we start orbit A at 35 meters per pixel. That is extremely high resolution from a planetary perspective. And then by orbit D, we're going to get down to 4 meters per pixel. So that is very, very high resolution. Now, what instruments are going to be on the Psyche spacecraft? Well, we have basically 3 remote sensing instruments. We have multispectral imagers, 2 of them for redundancy. We have a set of paired magnetometers on one of the booms. And then we have a gamma ray and neutron spectrometer. So the imagers are being led by ASU and Malin Space Science Systems in your hometown of San Diego. is the lead contractor for the development of the imagers. And these cameras will basically take images for morphology or shape of the surface, albedo or brightness, and also in color. So it has a clear filter and 7 color filters. And as I said, we'll be able to determine the topography by stereo imaging. Now, the magnetometers are being led by the Massachusetts Institute of Technology, and actually our colleagues at the in Denmark have built them. They are measuring magnetic field sensitive to 0.1 nanotesla, so that's very high resolution. So they're dual flex gate magnetometers on a boom. You have to put magnetometers on a boom away from the spacecraft so that the metal of the spacecraft doesn't interfere with the signal. The gamma ray and neutron spectrometer is built by the Applied Physics Lab at Johns Hopkins University, which is near Baltimore, Maryland. And these types of instruments measure, as I said, the elemental abundance of the surface, the amounts of iron and nickel and silicon and potassium and a whole bunch of others. And then the neutron spectrometer is what measures hydrogen, which is an indicator of water ice. And I've already explained how we use the gravity science experiment to determine the interior configuration. So this is just supplemental about how the instruments look and where they're located. The magnetometers, as I said, are on the boom, one of the booms. 2 of them separated by some distance, so you can get redundant measurements. The imagers are going to have a filter wheel, and I mentioned the fact of that. So there's 2 of them for redundancy. If one breaks, then the other one would hopefully work, and it has a digital electronics assembly, which is basically the computer boards that operate that. And there's a long heritage for these imagers from prior Mars missions. This is just a table that lists the wavelengths for each of the filters in there. So you have a broadband, what we call clear filter to image in sort of grayscale for the surface. And then each of these other filters in here is designed either to look for the minerals typical of silicate bodies, such as pyroxenes and olivine, or for specific sulfide minerals, such as oldamite, something we might expect on a metallic body. This just shows you the coverage of the surface in each of the orbits. So you see the footprints of the imager are rather big in orbit A at our lowest resolution, and then you start to get a greater coverage at higher resolution. The footprints, each one of these colors is a different orbital track, and it's very, very colorful when you get down to orbit C. Orbit D is not going to be able to get, we think, a close coverage, although we have designed the imagers so that they are pointed with an overlapping coverage in orbit D, so we could actually operate both imagers simultaneously to increase our coverage in the final orbit. And to measure composition, the gamma ray and neutron spectrometer. This is nuclear spectroscopy. Gamma rays are produced, neutrons are produced when cosmic rays and solar charged particles strike the surface of a body. It releases that material. These are measured by these instruments, and the signature that is produced is indicative of whatever element makes up the surface. And so we have specialists who will be doing that. And to complete the shape and gravity models, this is just going in, talking about the deep space optical communication to test that on our way out to Mars in that region. And then, using looking at the surface in 2 different angles during different orbits that allow us to produce the topographic models of the surface. So how did this mission get put together? Well, basically, Professor Lindy Elkins-Tanton and folks at JPL and some other colleagues first started having discussions in 2011. So that's 10 years ago. And they started discussing about what they would do for a spacecraft to visit this particular asteroid. And then NASA released an announcement of opportunity, basically soliciting proposals for discovery missions. So they submitted a preliminary proposal, and that won that proposal, along with, I think, 26 or 28 other proposals. So these all went to NASA. They were reviewed for the science content and the technical capability and the cost issues. And then NASA selected 4 missions to go to phase A, the proposal phase to develop the actual mission concept. So that was submitted in 2016. They was reviewed by NASA and looked at great detail. And then in January of 2017, NASA made the announcement that Psyche and Lucy were the two missions that were selected to become the next Discovery missions. So in January of 2017, we began phase B, formulation. This is where we really get into the details of the design. And we had a preliminary design review in 2018. We passed that. We went to phase C and D. This is the implementation phase. In 2020, we had our critical design review. And then we basically were bending metal and building instruments. And here you say, we are here in the middle of 2021 and in our final year preparing for launch. And then when we launch, and if we launch successfully in August of 2022, then we enter phase E. These are the operation phase. That is going to be the cruise phase for that 3.6 years until January of 2026 when we arrive and we really begin the science phase. So this graphic you see here is an example of what we call a hit and run collision, where you have something striking an asteroid and basically knocking off a lot of the crust and mantle, and you see some of the core fragments left behind. So this is to illustrate this concept of this is what we think happened to 16 Psyche after it was formed. And this is the very first artist concept painting of Psyche that was made for our proposal in 2017. And you can see here a very metallic body, heavily cratered, with what we think would happen when you have impact craters into a world made out of metal. You see some brownish, perhaps sulfur-rich stuff that was extracted from the core as it cooled. So I mentioned how one of the goals is, objectives is to see if Psyche was at once melted, we'll be able to tell if it's solidified from the inside out, like icy worlds and silicate inner planets, or did it go from the inside out? So like the Earth's core, where we have a solid inner core and a liquid outer core, so we're freezing from the inside out. The others are from the outside in, or could it be a rubble pile, a metallic rubble pile, or maybe something that was never even melted? So, you know, these are all possibilities here. So that was in 2017. January 2017 was when that proposal was selected. What have we learned since then? Because now we're in 2021. We've had several years past, basically, 3.5 years have passed. And since 18, 19, 20, actually 4 years, 4.5 years have passed. What have we learned about that? Well, our colleagues, our astronomer colleagues who do solar system astronomy, have been pointing telescopes of different types at asteroid 16 Psyche to try and get a better understanding of it. So the fundamental shape model is pretty well understood. You know, its effective volume, its effective diameter has been confirmed. They've tried to get better estimates of the density, and you can see as things as high as 6. But we've also had things that suggested it as relatively low. And, you know, so there's a very large range, but, you know, as they refine these values, the variation in density as recalculated here, the difference is the smallest is less than 25% the largest. What does that mean? Well, I'll mention that. They've also, based on the composition of what we think is going to make up Psyche, iron metal, a non-metal component, and if it has some porosity, if it has some void space in the outer crustal materials, given those densities, what is the compositional range that this asteroid could be? And, you know, there's a set of constraints that have come up from these studies between the volume percent metal and the volume percent pore space, and how much of the non-metal component could be there. This is all geochemical and physical modeling based on the data we have from telescopes. Thermal inertia is the resistance to change in temperature. Rocks tend to have, are very resistant to change in temperature, whereas dust, like in a desert, you know, when they're hot during the daytime, they cool down a lot at night. That's a physical property of planetary surfaces. Albedo, and in this case, radar albedo, how bright is the object? These are all things that have been measured from Earth-based telescopes. And so based on all of this put together, Professor Lindy Elkins-Tanton published a paper in 2020 suggesting that based on all this data, Psyche's bulk density appears between 3.7 and 4.2 grams per cubic centimeter. That's just the other version of these particular units there. Psyche is predicted to have between 25 and 60 volume% metal, which is a significant amount. The reflectance and optical properties indicate non-uniquely that the body may be largely metallic, but you could also have other stuff on it. And the interpretation of a metal surface is supported by density and radar albedo. So that very first painting of Psyche was one end member. These two views that you see here are some other possibilities based on what we've learned over the last few years. So on the left, you see the model of Psyche, where you see large amounts of metal, but there's also a significant amount of silicate material, the brownish gunk on the surface, that could have some pore space on it. And then the other possibility is the one on the right, where the metal and the silicate are more intimately mixed throughout the asteroid. So these three paintings, all done by artist Peter Rubin, show the potential end members of what this place might look like. So obviously this just gets us juiced up a lot more for wanting to get out there and actually have a good look and see. So how are we going to figure out what's what there? Well, there is no one measurement that can give us this answer. What you have to do is take information from all of the various sources and put it together. And this table is an example of that. So you can get the amount of iron sulfide and silicate materials from the multispectral imager and also from the gamma ray and neutron spectrometer. The gamma ray spectrometer will measure the amount of nickel in the surface. The magnetometer will tell us the type of magnetic field. And if it has, sort of these patches here, this is one possibility. If you have these information here, this is another possibility. If you have these possibilities in the third column, you have a third possibility, and then you see over there on the last column, the other. So you can see for the four different possibilities that were considered at the time we wrote the proposal, and how the different data sets will indicate one versus the other. Here's another way of looking at that. So the big question is Psyche a core or primordial unmelted material? And you can see the measurements from the magnetometer, the nickel abundance from the gamma ray spectrometer, and other information from the imager can lead you to these different conclusions about it. Now, this is one set of possibilities, but of course, it's probably not everything. What if it's something else? Well, that's what makes planetary exploration exciting, is if you discover something that's totally unexpected, and that just demonstrates how nature is even more complex than what you expected. And to be honest, in every NASA flight mission that I've worked on, and I've been working on them since grad school, we've always discovered something unexpected. And it's made it really exciting to figure these things out. So if Psyche is a metallic object, what do impact craters look like when they strike a world made out of metal? Here's one example. This is from the Ames vertical gun. This is where you basically have a high-speed gun. You put in a projectile, a metallic projectile, and shoot it at different types of targets. And here's what happens when you hit a metal target. You do form an impact crater, but the metal sort of quickly is ejected and freezes. And so you have the sort of a lip of an extended, it's not loose impact ejecta. It's actually a metallic rim around the craters, although you do actually get some metallic ejecta formed from some of these things. Parts of the surface could be made up of pallicides. That would be really exciting if you have a strong detection of olivine, which the multispectral imager should be able to measure, and have metal in close proximity. That would suggest that Psyche could be the pallicide parent body, or one of them anyway. So what is the current status of the Psyche mission right now? Well, this is one of the clean rooms at NASA's Jet Propulsion Laboratory, just up the road there in Pasadena, California. And you see the main body of the spacecraft as it was assembled by Maxar Technology, and they're located near Palo Alto. And then they put this on a truck, and last summer it was shipped down there to JPL. And you can see this is where we're doing the integration. We're slowly adding the instruments to it. At the time that this photo was taken, you see the magnetometers over here are on board on this boom over here, and they've got the fittings over here for the gamma ray and neutron spectrometers. And then these plates over here, these two square silver plates above these two red canisters here, those are the mounting plates for the multispectral imager. Since this image was taken, the gamma ray spectrometer and the neutron spectrometer have been added to the boom, and they've been doing some work in there the multispectral imagers are going to arrive before the end of the fall. And over here, you see the ion engine thrusters on that. So I have a video to show you of the Psyche exploration that'll be at the end here. But let me just talk a little bit about some of the other missions that are going on really quick. So OSIRISRex, I'm sure you were following that in the news. ASU was very heavily involved with that mission. It successfully collected its sample of asteroid 101,955 Bennu, a near-Earth asteroid, and that spacecraft is on its way back to Earth to drop the sample return canister here in 2023. Same with the Japanese Hayabusa 2 mission with the samples from Ryugu. Now, the next major thing that's coming up in just another month or so is the Lucy mission, our sister discovery mission, and 2 ASU professors, Phil Christensen and Jim Bell, are co-eyes on this particular mission. This mission will be the first spacecraft to visit the Trojan asteroids. And here you see a map of the solar system, the sun and the Earth, and Jupiter's orbit about the suns. And you see the 2 patches of Trojan asteroids out at L4 and L5. And so this trajectory, which was made a couple of years ago, shows the path of the spacecraft is designed to go out and visit multiple asteroids in each of these populations here. So the idea is to characterize these Trojan asteroids in a way that has never been done before by spacecraft. All we know about them is from telescopes. So, you know, with all this talk of asteroids and metal asteroids, it's logical to ask questions about mining, the value of these asteroids. Asteroids contain valuable resources to build a spacefaring civilization. If you've explored this online, I'm sure you see interesting graphics and thoughts about how companies might be able to do that. Dr. Elkins-Tanton a few years ago made an interesting calculation based on the size of Psyche and assuming it's made of iron and nickel and the appropriate trace elements typically found in iron meteorites. How much would it be worth? And we came up with a figure of 100,000 times the gross national product of all nations on Earth, or 10,000 quadrillion dollars. Now, obviously, if you got all of that metal and brought it back to Earth, that would crash the markets and all that stuff would become immediately worthless. So some fun games playing with the economics of it. But the point of this is that if there are valuable metals out there on Psyche or other resources on near-Earth asteroids, these are useful things that humanity can utilize in the future. Now, to mine asteroids is not an easy task. You just can't hook a spacecraft up to one end of an asteroid and suck it in and out comes fun stuff, useful stuff. It's going to be much, much more complex than that, particularly for humans to work in microgravity of an asteroid body. That's something that hasn't been done yet. But it's been interesting to speculate how companies like Planetary Resources has said, you know, this is something that can and will be done in the future, whether it's for metals, whether it's for silicates, building materials, whether it's for water, whether it's for energy source like helium-3 in the lunar soils. These are all things that could be useful in the future as we build a spacefaring civilization. So let me summarize my presentation here. Asteroids are the rocky remnants from the formation of the solar system. On January 4th, 2017, NASA selected Arizona State University to lead a Discovery class mission to the metallic M-class asteroid 16 Psyche. NASA's Psyche spacecraft, just like the Dawn mission, which I worked on previous decade, will use solar electric ion propulsion to move through the solar system to get out to the asteroid. Psyche will carry 3 instruments, visible multispectral imagers, magnetometers, and gamma ray and neutron spectrometer. The Psyche spacecraft was built by Maxar Technologies. It was delivered to the Jet Propulsion Lab this past summer. It is getting ready for integration and testing as they continue to add the instruments to it, a process we call ATLO, assembly testing and launch operations. That'll go on until next summer when they package the spacecraft up and ship it to the Cape for its eventual launch. And it is going to be launching on a SpaceX Falcon Heavy. I didn't mention that. That's something we know now since then. So the launch date is August of 2022 with a 3-year cruise phase and then a 20-month, what we call nominal mission that'll begin hopefully in January 2026. So stay tuned as we continue with development of this. And I think here's a short video to watch here.
Is there sound?
Is there sound with this video? Can we turn on the computer sound perhaps?
Oh, well, there is music. I do have it up on mine.
When
The
you
sound
share
isn't.
when you share your content, there's in the lower left-hand corner is share audio and optimize for video content. Easy enough to do. If you unshare your application, and when you reshare it again, you'll see in the lower left-hand
Yeah.
corner.
The music's not that important. I'd rather continue with it if I can. Those are the types of things you need to tell me how to do it before we start.
We all know how the Blue Danube goes anyway.
Yeah.
Wow.
So you can download this video yourselves and watch it. It's available. It's at the JPL Psyche side or the NASA Psyche side or the ASU Psyche side. So psyche.jpl.nasa.gov is probably the easiest one to get it from there. That's it. Let me stop sharing, and we are back here so I can see people. And I thank you for your attention. I hope you found this presentation useful, and I will be here for as long as you want to answer questions.
That was a very interesting presentation. You didn't mention carbon. I'm remembering Engineering Materials 101. And if you have hot iron and carbon, you're going to get all kinds of different compositions of, pig iron, probably never steel, or some bloomery process or something. Do you expect to find different alloys of materials?
I don't think so. I think what we expect, just based on the information we have right now, is iron, nickel, maybe platinum group elements in there, probably sulfides extracted from it. And then, from the crust or mantle that was there, we might have some of the silicate type of materials. The only carbon-related materials that I would think might be the impact of carbonaceous chondrite meteorites or asteroidal material that could be deposited on the surface in some areas. So we are planning on having the ability to search for that as well. So yeah, that's what we'll be looking at. But I don't think I've heard any discussion of iron carbon alloys as a major component that we'll be searching for. I see there's questions in the chat. Do you want me to go through that?
Yeah, sure. Go ahead.
Rock and roll.
Okay. Let's see. Some people saying hi. From David Alvarez, question, do you think that it will ever be on a course to hit Earth? No, absolutely not. Psyche is at the far end of the asteroid belt. It is in a very, very stable orbit. Jupiter's gravitational influence doesn't really hit that particular part of the main asteroid belt. There's zones that it does influence. There are resonances. And if something falls in that resonance, then Jupiter usually kicks it out of the asteroid belt that could come toward us. Psyche is nowhere close to that. So the asteroid Psyche is no threat whatsoever to Earth. Phil asked, since the science orbits get lower and lower, how will you dispose of the Psyche spacecraft post-mission? Well, that's an excellent question. Usually after what we call the nominal mission ends, we take a stock of the spacecraft and how much fuel, how much power it has left on it. And typically, NASA will approve what is called an extended mission for some period of time. And that extended mission could involve us dropping even lower in orbit around to get additional information about Psyche. With the asteroid, the near Shoemaker mission, which went to asteroid 433 Eros, they ended the mission by actually able to slow the spacecraft down enough and have it soft land on the surface. I sort of don't think we're going to be capable of that unless we can use the ion engines to slow down and then turn it into a lander. But the other possibility is if we have enough fuel and resources, we could fire up the ion engine and go outward and depart Psyche and then visit another object in the solar system and try and characterize that. We did propose that for the Dawn mission after we finished the Ceres encounter, but NASA insisted that we use up all the spacecraft resources to study Ceres and get additional information. So how we dispose of the spacecraft would be, it would probably be boosted up into a 50 to 100 year stable orbit, you know, and then ultimately it would crash on the surface. And that has less implications for a metallic body than it would for an icy body. So the next question, what is the rationale behind hard landers? Well, basically, when they started doing hard landers, the first was the Ranger series to the moon in the mid to late 1960s. And that's when we were trying to figure out how to land at all. So smacking something into the surface and you get imaging as you get closer and closer and closer. And then, you know, you hit the surface and you're done. So it was basically, that's what you can do. You know, that was the technology developed before they invented soft landers. Question 2 is, would an impact from an M-type asteroid cause more damage than an impact from other types of asteroids? Yes, the amount of damage you would have if you have 3 asteroids of the same size, but one was metallic and one was stony iron and one was a stone, just rock. The one that hits the hardest, that travels the fastest, that has you know, that one would probably cause the most damage. So yes. How fast is Psyche spinning? I think I said it rotates on its axis. What was it, about 4.1 hours or something like that? That was earlier in the slides. Joseph asked, is DSOC a new technology and does it offer any benefit, or is it simply a communications backup? It is a new technology, deep space optical laser communication. It has been tested, I think, Earth to International Space Station. It'll probably be tested on the moon during the Lunar Gateway project when we go back to the moon later this decade. And then, you know, we're going to test it out to Mars distance. So is it a backup? Yeah, right now it is a backup, but it could also, depending on how successful it is, be a second primary form of communication in addition to the deep space network. That's I think what the ideal expectation is. Aziz, regarding slingshot method of accelerating a probe by close flyby with a planet, why is the momentum transfer during approach and deceleration past flyby not symmetrical? Why is there a net momentum transfer to the probe? Is there a simple way to explain this? And does a probe approach a planet with or against the planet to pick up momentum? Those are all excellent questions, and I do not know the answers to most of them. All I can tell you is that you know, all of the flight missions I've worked on, with the exception of Magellan. I actually worked on Magellan at Venus when I was a grad student, and I was in grad school the semester we launched the Galileo Jupiter orbiter probe. That was October of '89. And, you know, after the Space Shuttle Challenger accident, they got rid of the big liquid fueled booster for Galileo. So they had a solid booster, but it didn't have enough energy to send Galileo on a direct to Jupiter trajectory, which would have gotten it there in 2 years. So they redesigned it with a Venus Earth gravity assist. So they shot the Galileo spacecraft inward. It did a Venus flyby, came out, did an Earth Moon 1 flyby, flew by asteroid Gasper in the main belt, then came back around, did Earth Moon 2, and then did a flyby of 243 Ida, and then it had the momentum to get out to Jupiter. It was there when Comet Shoemaker-Levy 9 hit Jupiter, and then got to Jupiter in let's see, that was December of 1995, if I remember correctly. So all I can tell you is that it's an effective momentum transfer. The amount of transfer from the planet is so minor, it's inconsequential, but it does give the momentum boost to the spacecraft. And NASA uses that quite a bit, where, you know, the cost of all that extra fuel, the mass, would make missions too expensive. The next question, could you analyze from Earth, assuming the lander is completely destroyed, the materials kicked up from the surface of a hard lander? Oh, you're interested in hard landers, huh? Actually, yes. There was a lunar mission called, what was it? Where they sent a spacecraft with a booster, and then they turned it around and they left the booster ahead of it, and it impacted into a region of the South Pole that has the craters and permanent shadow where we think the water ice is.
Mhm.
And then the spacecraft behind it was imaging the plume that came up from that impact before it actually impacted too. I can't remember what the name of that mission. It wasn't Laddie. It was L-Cross, the L-Cross mission. So that, I think, happened at the same time, or nearly the same time, that the Lunar Reconnaissance Orbiter was launched, which was in 2009. So if you search the NASA L-Cross mission, you can probably get some of the basic information about that. Okay, that's all the questions in the chat. Are there other questions there online or more for the chat?
David, I noticed in the background there, you have a model of the attack lander flown by the colonial Marines and aliens. Is that what's on your back desk there?
No, that is a model of the Rocinante from the TV show The Expanse.
Ah, okay.
Yeah. Yeah, I'm a big Star Trek fan. I tell people that when I was a kid in the 1970s, I grew up and the original Star Trek series was syndicated 5 nights a week. So it was on in the afternoons when I got home from school, and watching those same 79 episodes over and over again inspired me to want to become a planetary scientist. So I went to school at Indiana University and I majored in astronomy and astrophysics. But I came to learn that most astronomers don't study stuff in the solar system. They study stars or galaxies or nebula or cosmology. And I wasn't interested in that. I was interested in what the Star Trek crew visited, which was planets. And so I was taking a geology class, and there was a planetary geology professor there. And he said, well, you know, there's this whole field called planetary geology where we study the surfaces of the planets and moons and asteroids of our solar system using NASA robotic spacecraft data. And I said, no, but that's what I want to do for grad school. So that's what I switched into in grad school. That's what led me to ASU and to have my involvement with NASA flight missions. And, you know, here I am today.
Hence the Star Trek Enterprise up there.
Yes, that is the Enterprise from Star Trek Discovery.
I was going to ask you the very same question. How did you get involved in this? But how about a slightly different flavor? I would guess these are very multidisciplinary teams because you've got the geology, the spacecraft, mechanics, and all that sort of thing. What's it like to work on a team like this?
Well, that's an excellent question. And I think it's quite fun because, and particularly the Psyche mission, our PI, Dr. Lindy Elkins-Tanton, she was the former director of our School of Earth and Space Exploration. And before that, she was the director of the Carnegie Institute of Terrestrial Magnetism. And she's very big on promoting interdisciplinary research and commonality. On Psyche, we don't have a science team and an engineering team. We have a team, and we all work together. So we have, at this point in the mission, is being very much led by the engineers who are building the spacecraft and working out all the techniques on how we'll operate the spacecraft, how we'll communicate, how we'll run all the instruments. But the scientists are there too, and our job, because we're going to have to take the data and analyze it, and from that answer all those scientific questions. My particular job on the Psyche mission, I am a geologic mapper. I make geological maps of the planets and moons of the solar system from the imaging data, and from that determine the geological histories of these objects. And that'll be my job on Psyche when we get there. So it's very, very fun. Right now, when we have our team meetings, we have both science and engineering together so that everybody learns a little bit about what everybody else is doing. So we all have a much better understanding about how all this is being pulled together. And that's sort of a paradigm that our whole department at ASU, that's why we're called a School of Earth and Space Exploration. We have both geological sciences, planetary sciences, astronomy and astrophysics, and systems engineering all together in one department. And our mantra is to create scientists with a knowledge of engineering and engineers with a knowledge of science, so the two can work together better to help build the instruments, techniques, and spacecraft to better explore the Earth, the solar system, and beyond.
Somebody asked, did you have a telescope as a young man? And I'll amplify that by saying, since you're the imager lead, do you have a telescope with a camera on it?
Yes, my father gave me a used refractor telescope. And matter of fact, I still have it here at my home, and I got it out to observe the comet, the last comet that we could see here. I don't have a fancy telescope like all of what you guys have. They're the ones that are several thousand with the cameras and all that type of stuff on it. One of the reasons I switched from astronomy into planetary geology is I don't like staying up late at night. I would much rather work with the data that comes down from the instruments on the computer during normal daylight hours. Yes, I did have a telescope as a young man, and I still have it. Other questions?
Questions? Let me ask a question about the spacecraft. Just from what you showed, there are some that would be, I wouldn't call it COTS, but it's space qualified standard equipment. And some are probably things that have been developed specifically for this. Everything has a little bit of a prototype quality.
Absolutely. Yeah, as new technology becomes available, it has to be tested on Earth, and it has to be tested in space in near Earth orbit. It has to reach what is called a certain TRL. That stands for technology readiness level, before it'll be deployed on a multi-million-dollar, or in some cases billion-dollar spacecraft. So there's a lot of what we call heritage in the systems that we have on these spacecraft. And in particular, the Psyche spacecraft is very, very similar to the Dawn spacecraft we sent to work to study Vesta and Ceres in the prior decade. It uses solar electric ion propulsion. It's a little bit different in its operations, but it's also well established from the propulsion that Maxar uses on its Earth orbiting satellites. The avionics, the computers, all of those main systems have very good heritage. The fundamental design of the imagers and the gamma ray and neutron spectrometer and the magnetometers are basically similar but improved designs of things that we have flown on NASA's flight missions for the last 30 years. So we do tweak that with new technological capability as it reach that higher technology readiness level. But there's an awful lot of heritage on the spacecraft from all of the past. We build on all of the past missions. A question there from Aziz. What is the Psyche probe's projected lifespan, and what is the limiting factor? Is the power source nuclear or solar? It is solar panels, yeah. Nuclear radioisotope thermoelectric generators are used either in places where you're too far from the sun and you can't get enough solar power, which is in basically the outer solar system. We successfully can use solar power at Jupiter now because of the improvement in technology. It's been suggested we might be able to use it at Saturn, but the Dragonfly mission will have an RTG on board, and anything that goes beyond Saturn has an RTG. The Curiosity and Perseverance rovers, for their long driving time, long operations time on Mars, also use RTGs. But Psyche will use solar panels. And its projected lifespan, that's a good question. It depends on how much we burn through the xenon fuel and the cold gas for the cold gas thrusters that we use for maneuvering. But, the solar panels don't degrade that fast. So it would be our expectation that after our 2-year nominal mission, after flying through space for 3.4 years, we would still have capability to continue to function for some years after that. Now, how many years like that is hard to say. If there's a technical problem that might cause us to have to consume our consumables at a faster rate, then that might not be the case. But, take a look at the Voyager spacecraft. They have RTGs. They launched in 1977. They're out beyond the Helios sheath now. They're still capable of sending back really weak signals, and that's been a long time ago. So I don't think we would last that long, though.
David, do you expect to be on the program for the entire length of the satellite's lifespan, or would you move over to another program?
Generally, when you're a member of the science team, and this is actually the first NASA mission that I was on the science team on the initial proposal, the Phase A proposal that was submitted to NASA and was selected. So I would theoretically be on this mission until the very end of the mission. And it is my intention, I'm not that old, that I should be able to stay on this mission until its very end. All the other flight missions I worked on, I was either a student and joined after the mission launched, or the Dawn mission last decade, I joined as a participating scientist for the Vesta mission. And that was about 6 to 8 months before we arrived at Vesta. And then I was added to the science team as a full team member for the Encounter with Dwarf Planets series. And I was involved with that until we ran out of fuel and the mission ended. So I'm hopeful. I would expect to be on until the mission ends. Now, missions that have much longer time spans, like Europa Clipper or the Jupiter Icy Moons Explorer of ESA, you know, those missions could go long. If you're a senior person in your career, you may not live long enough to see the mission to the end. And that's where there's a policy of bringing in younger scientists as team members who would be around, you know, for the full length of the mission. So that's something that NASA has made a point of working to improve over the last 10 years or so.
Your objective seems to be very technical and confined, if you will. Have you got any notion of like a blue sky discovery that you might run across? Unlikely, but dramatic.
Well, I suppose, you know, discovering evidence of extraterrestrial intelligence or something crashed on a planetary body is something that we all would have deep in our back minds of something that could happen. But so far, I've been on missions and I've explored enough of the new worlds of the solar system that we've never found anything that's like that. For Psyche, you know, I sort of I think it might be some exotic material, a mineral or surface feature. That would probably be something that would be unexpected that we might discover there. I think if something like that were to occur, it might occur, you know, if the Europa Clipper catches a really good plume on Europa in process there, or an eventual mission to Enceladus has the right instruments and it discovers some sort of a biological material and the plume material coming out of the Enceladus plume to the South Pole. Those are the types of really great, you know, life-changing events for everybody that one could anticipate on something like that. But, you know, how likely something like that would be is really, really hard to say. Is the project supported by international partners or USA only? I missed the first part of the talk. My apologies if you already covered this. I didn't specifically mention that, except for the fact the Psyche mission is almost entirely US. We do have an international partner from Denmark. The Technical University of Denmark built the magnetometers on our spacecraft. So those are the primary international partners for technology. And then for our imager development, we're working with the German Aerospace Center in Berlin. They have a team that is top-notch at creating digital elevation models or topographic models of the surface based on imaging data. I've worked with these folks since 2003 on the European Mars Express orbiter, and I also worked with them on the Dawn mission because we had a German-built camera and an Italian-built spectrometer on the Dawn mission. So, you know, different missions have different amounts of international involvement. But Psyche, yeah, our only international involvement really is the Danes who built our magnetometers. Other questions?
Any more questions? Well, maybe not. I'd like to thank you for this outstanding talk and the Q&A session afterwards. You're very engaging, and it looks like you're going to have a lot of fun with the science for many years to come.
Well, thank you very much. I enjoy doing these talks. I do quite a few of them every year to different groups. I talk to the Phoenix Astronomical Society at least once a year. I've talked to other astronomy clubs as well as other community groups here. So I really enjoy it. I'm very happy if you guys enjoyed the presentation. I hope you got out of it. I tend to talk really fast, but hopefully between my talking and the slides, you got a lot of information out of it. And stay tuned, keep your fingers crossed for our launch, that we hit our launch window on time next year. And, then a few more years down the road, I hope we have some very interesting discoveries that we can talk to you about.
Well, thank you very much. And if there's anything the astronomical community, the amateur scientists and so forth can do, we'd be glad to step up.
I'll be happy to pass that information along to our PI.
Okay.
Thank you, David.
Thank you very much. I'll sign off now. Thank you very much. Have a great rest of the week and upcoming weekend.
Goodbye and thank you.
You're welcome.
Great job.
Thank you. Bye. Very good.
Bye-bye.